Welcome to the fifth lecture of optical sensors course. In the third and fourth lectures, we discussed what are electromagnetic waves, and we also saw that when the wave is propagating in certain direction, the electric and magnetic field components are perpendicular to it, and they are also orthogonal. So, it becomes kind of right angle triad where electric field, magnetic field and the direction of propagation are perpendicular to each other. And we saw that when a wave travels in a certain direction, we can have 6 components of electric and magnetic fields in total, and out of these 6 components we can have 2 sets which are called transverse electric and transverse magnetic polarizations, and this makes our life easy because it is very important to see that when you have 6 components, you solve for vector equations, you need to have 6 equations, right. Here you can reduce it to 2 by considering 2 sets of solutions, and these are actually orthogonal polarization states which we saw, and we also saw any random polarization can be resolved in these 2 parts. Now, we move ahead and see what happens when these waves travel from one medium to the other medium. So, today we are going to discuss the reflection and transmission at interfaces. We will solve for Fresnel equations. So, you know that electromagnetic waves in free space is the most simple case, where we consider that there is no charge, no magnetization, no polarization and no currents. So, all was 0. So, basically rho external, J external and P and M, this all was equal to 0 for free space. But when there is a matter, say for example glass, then we need to consider certain properties which are either dielectric, magnetic or conducting properties. We discussed about the constitutive relations while describing the Maxwell's equations, and from there we can see that this one takes care of the dielectric ones, this one takes care of the magnetic one, this one takes care of the metallic ones. For insulators, this is equal to 0. So, if you have a dielectric or magnetic medium which is non-metallic, which is non-conductive, then you have sigma is equal to 0. So, you take this kind of material and let us see what happens to insulators. So, in insulators we know that there was epsilon and mu. Just replace epsilon naught with epsilon and mu naught with mu. So, the speed of light which we saw was c was equal to 1 upon under root epsilon naught mu naught. Now, c for the medium, let us say v, it becomes 1 upon under root epsilon and mu. You can always write epsilon as equal to epsilon r into epsilon naught and mu is equal to mu r into epsilon mu naught. This is relative. This is relative permittivity. And this is relative permeability. So, what you see here that basically we can write V is equal to 1 upon epsilon r epsilon naught into mu r mu naught. We can take epsilon r and mu r outside. So, it becomes under root epsilon r under root mu r into 1 upon epsilon naught mu naught. this is equal to C. This, if the material is non-magnetic, mu r is equal to 1. Basically, mu becomes equal to mu naught. So, 1 by under root epsilon r is equal to 1 by n. N is the refractive index of the material. So, from here you get V is equal to C by n, right. So, speed of light in a material medium gets slightly decreased, and it is by slightly a factor of 1 by n, that is the refractive index of the medium. So, denser the medium, denser means a medium with high refractive index will have smaller speed of light. So, the speed of light changes. So, you get C by n, you solve for the Maxwell's equations, from there you get to this equations for electric field and a magnetic field. I wrote in slightly in different form, and that was del 2 E del 2 E is equal to 1 upon C square into del 2 E by del T square. You can write it del 2 E is equal to 1 by C square. Now, in this present case it will become 1 by V square into E double dot. Okay. So, that is what we have written here, and you can write it in this way. You can solve for plane wave like solutions which are similar like what we have previously, and now you have here omega is equal to k by V. Power density is given by this relation, where Z was equal to impedance of the material. So, if you have Z, 0 was equal to under root mu 0 upon epsilon 0, and Z equal to basically mu upon epsilon, which is here, you can have equal to mu r upon epsilon r into Z naught. So, you know the impedance of the material. We have certain boundary conditions when a light wave goes from one medium to the other medium, there is an interface. So, suppose I have one medium here which has refractive index n1, or maybe epsilon 1 mu 1 from epsilon 2 mu 2, it goes from epsilon 1 mu 1 to epsilon mu 2. What will happen? How will electric fields and magnetic fields E and H in this one will behave to E2 and H2? What is the relation between them? So, that is called boundary condition. So, at the interface of these two media, the following boundary conditions apply to the electromagnetic field. And what are those? The tangential component of the electric field are continuous. So, tangential component here which is along the surface, component of the electric field which is along the surface in these two is the same. So, electric field in tangential component in the first medium, electric field tangential component in the second medium, they are equal. So, that is why they are called continuous. However, the tangential components of the magnetic field are not continuous, they are discontinuous. What it means that if you solve for the, this is first one, this is the second one, the tangential component here and here, H1, H2, H1 is not equal to H2, the tangential component. this is equal to 4 pi Js by c. Js was the surface current. So, if Js is equal to 0, then it will be valid, otherwise it is discontinuous. The normal component of the magnetic induction B is always continuous. What is normal component? Normal component is the component which is normal to this interface. Tangential component with the component of electric and magnetic field which are along the interface. Normal components means the components which are normal to the interface and they are here continuous. However, for the displacement they are discontinuous. So, they are continuous only in the absence of charge and they change abruptly if you have any amount of charge, surface charge density. So, if you have a small charge density, then they are not continuous, otherwise they are continuous. So, these are the boundary conditions we will be using when we see that light goes in from one medium to other. So, let us talk about the interface of two insulators. We have here an interface of two media, this is interface, light comes from here. So, the dielectric properties are epsilon 1 mu 1 here of the first medium, epsilon 2 and mu 2 for the second medium. The k vector of the incident light in this direction, that is perpendicular to the interface. So, the B and E components are shown here with red and blue curves. A fraction of this incident light gets transmitted along this direction and a small fraction comes back. So, I have put it here that you can see that a small portion is reflected. I denotes the incident, R denotes the reflected ones and T denotes the transmitted ones. So, you have here reflected and transmitted fields and now you apply the boundary conditions. So, it is similar to the case like light hits a glass window, light falling on it at 0 degrees. So, boundary conditions are E must be continuous, that EI plus ER is equal to ET, because this is a parallel component. You see this is along the interface. So, it must be continuous. So, the electric fields at this side and electric fields at this side should be continuous. H must be continuous because there are no surface currents. So, this is also continuous. So, using this relationship we come to this continuity of H. You see that you can use this relation and equate x, y and z component to find out what is E y and H x, and you will see that they are having opposite signs. So, y here we have minus, here it is plus, but here it becomes minus when it is written in terms of E, because when it is propagating in plus z direction, E x and H y have the same sign and the opposite for the reflected wave. So, if it is having same sign when it is moving in one direction, opposite sign when it is a reflected wave. So, that is why for ER you have minus sign here. Okay. So, you solve for Fresnel reflection and transmission. Now, the problem was reduced to two equations in E r and E t. You have to actually calculate the ratio of E r by E I and E t by E I, and if you solve it you come to this equations E r, E t, H r, H t and S is the Poynting vector. So, now you know in terms of the impedance, Z is the impedance, yeah. Z 1 is under root mu 1 by epsilon 1, Z 2 is under root mu 2 by. So, you know this. So, in terms of the impedance you get this formula, and from here you can calculate the reflectivity and transmittivity, but we want to write it down in terms of reflective indices. Because when we are dealing with optical surfaces, optical media, we do not want to have these equations in terms of Z, we want to have them in terms of refractive indices n. This is what it looks like. So, in a similar manner using Snell's law we will prove it now only, and if you have this kind of Snell's law, the Rs and Ts and Rp and Tp are given by this relation. So, let us try to derive them. So, let us consider an interface of two media, and we have refractive indices n1 and n2 for media 1 and 2, and it has also epsilon 1 mu 1, epsilon 2 mu 2, and we consider that an electromagnetic wave is incident at angle theta 1, a part of it gets refracted at angle theta 2, and part of it gets reflected, let us say that this is angle theta 3. So, if it has wave vector k 1, let us say, and this one is k 2, and since it is in the same medium, let us again write it. First let us write it k 3, but it will be equal to k 1 only. So, and I consider that this is x axis, this is axis z, and y is pointing upwards. So, it is like this x, z and y. So, I have already told you that if we have an electromagnetic wave incident at some structure, what you have to do is that you need to solve electric and magnetic fields, and they will have 6 components in total, but you can always have a 2 independent set of solutions that were called TE and TM solutions. So, for this kind of configurations you will have H x E y H z as TE mode, and E x H y E z at TM mode. So, that is defined like you have this plane of incidence, and this plane of incidence sees the change in refractive index, then the component which is perpendicular to the this kind of plane of incidence, if it is the electric field component which is perpendicular, then you say it is TE mode, and if it is the magnetic field component which is perpendicular to this kind of plane, you call it TM mode. So, we have this kind of wave, and let us say that we consider here only TM mode, and for this kind of mode the electric field vector lies in the plane of incidence. So, let us consider that the electric field is pointing in this direction E I, and the magnetic field is perpendicular direction H I. The one which gets transmitted has electric field E T, and the magnetic field is H T, and suppose it has in the reflection it has E R and H R. So, let us say that if the equation for the plane wave which is incident is given by this is E I is equal to E I 0 e to power I omega t minus k dot r. So, it is k 1 dot r, and the one which is reflected, let us say that E r is given as E r 0 e to power I omega prime t minus k 1, which I told you that it is k 1 because k is equal to omega by c into n, and if it is the same reflective index medium, the k will be the same. So, okay. So, it is k 1 dot r and E t equal to E t 0 e to power I double prime t minus k 2 dot r. So, if a plane wave is incident at an interface of two media having refractive indices n 1 and n 2, you can have partial reflection and partial transmission through this interface, and the electric field components of reflected and transmitted light are given by these relations. So, if you resolve this k vector parallel and perpendicular to this interface, you can write it like E I is equal to E I 0 e to power I omega t minus k 1 cos theta 1 x minus k 1 sin theta 1 into z, and similarly E r will be E r 0 e to power I prime t minus k 1 cos theta 1 into x minus k 1 sin. So, it is theta 3 actually. So, cos theta 3 sin theta 3 into z, and E t is equal to E t 0 e to power I omega double prime t minus k 2 cos theta 2 into x minus k 2 sin theta 2 into z. So, we have this kind of waves. Now, we apply boundary conditions. So, if you apply boundary conditions, and what are they? The boundary conditions: E parallel along the interface is continuous. So, it means that E parallel in medium 1 is equal to E parallel in medium 2 at x is equal to 0. So, what is the component of E in this direction? So, if you have theta 1 here, so it will be like this angle theta 1. So, if you take this, again it will be 90 minus theta. So, it will be sin theta, or so you can have this actually, and this is theta, this is 90 minus theta. So, actually this will be theta 1. Okay. So, you can write that E I O cos theta 1 e to power I omega t minus k 1 cos theta 1 into x minus k 1 sin theta 1 into z, minus, because you have theta 3 here. So, this will be theta 3. So, this will be 90 minus theta 3, and then you have theta 3. So, it will be not minus, it will be plus E r 0 cos theta 3 into e to power I omega prime t minus k 1 cos theta 3 into x minus k 1 sin theta 3 into z equal to E t 0 cos theta 2 e to power I omega double prime t minus k 2 cos theta 2 into x minus k 2 sin theta 2 into z at x is equal to 0. So, at x is equal to 0, E I 0 cos theta 1, that is the tangential component, into e to power I omega t minus k1 sin theta 1 into z minus E r 0. I am removing the vector sign because you can put it always, but let us be more that was omega dash or omega 2, omega dash. Let us check. So, omega dash t minus k1 sin theta 3 into z is equal to E t 0 cos theta 2 e to power I omega 2 t minus k 2 sin theta 2 into z. So, these equations, this equation is satisfied for all times only when omega is equal to omega dash is equal to omega 2. Why? Because for all the times for t is equal to constant, for all the values of t will be the same, all the omegas have to be same. So, this is the first condition, that this condition should be satisfied. Now, let us omit all these things. What you get here? What you get here? Also, we see that k1 sin theta 1 is equal to k3 k1 sin theta 3 is equal to k2 sin theta 2. Why? To satisfy this boundary condition, all this should be equal. That means, since it was k1, we will have sin theta 1 is equal to sin theta 3, which is not always, but like theta 1 is equal to theta 3 for acute angles. We know that all are acute angles. So, this is true. It is the Snell's first law. Snell's first law, law of reflection. So, theta 1 is equal to theta 3, that means the angle of reflection is equal to the angle of incidence. And what we get is that k1 sin theta 1 is equal to k2 sin theta 2. That is Snell's second law. You can simplify it bit. So, it will become n1 sin theta 2, because you know that k is equal to omega by c into n. So, you can write omega by c into n1 sin theta 1 is equal to omega by c into n2 sin theta 2. This cancels out, you get n1 sin theta 1 is equal to n2 sin theta 2. This is another form of Snell's law. So, if you put these things in equation, this one, say let us say this is equation 1. So, put all this in equation 1, what you get? E I naught, E I 0 cos theta 1 minus E r 0 cos theta 2 is equal to E t 0, sorry, cos theta 3, which is cos theta 1 actually. So, you can write it cos theta 1 is equal to cos theta 2. This is equation A. You can write, you can further simplify it. Cos theta 1 EIO minus ERO is equal to cos theta 2 ETO. Basically, this is one. What is the second one? The tangential component of electric field. Let us say what happens with the tangential component. Tangential. Displacement vector. So, dI plus dr in this direction must be equal to dt this direction. So, x means the normal component. So, it is not the tangential one, it is the normal component. So, you are having the normal component of displacement. Let us see what happens. So, you write it like this minus epsilon 1 EIO sin theta 1 minus epsilon 1 ERO sin theta 1 is equal to minus epsilon 2 ETO sin theta 2. You can simply write it as epsilon 1 EIO plus ERO into sin theta 1 is equal to epsilon 2 ETO sin theta 2. This is equation B. Now, let us simplify. Equations A and B. What you get? We want to calculate ERO by EIO, which is the amplitude reflection coefficient is equal to RP. Amplitude reflection coefficient. We want to calculate RP, and that comes out to be epsilon 1 sin theta 1 cos theta 2 minus epsilon 2 sin theta 2 cos theta 1 divided by epsilon 1 sin theta 2 cos theta 1 plus epsilon 2 plus epsilon 1 sin theta 1 cos theta 2. This is RP. What is the amplitude transmission coefficient? Amplitude transmission coefficient, that is Tp, that is equal to Et0 divided by Ei0, and you get 2 epsilon 1 sin theta 1 cos theta 1 divided 2 epsilon 2 sin theta 2 cos theta 1 plus epsilon 1 sin theta 1 cos theta 2. Now, we know n1 sin theta 1 is equal to n2 sin theta 2. We can write it in terms of n. So, Rp is equal to, it was under root epsilon 1 into under root epsilon 1 sin theta 1 cos theta 2 minus under root epsilon 2, you can write under root epsilon 2 sin theta 2 cos theta 1 epsilon 1 sin theta 1 cos theta 2 plus under root epsilon 2 sin theta 2 cos theta 1. We know that n1 sin theta 1 is equal to n2 sin theta 2. So, we can write it actually under root epsilon 1 sin theta 1 is equal to under root epsilon 2 sin theta 2. From here we can substitute, what we get is n1 cos theta 2 minus, you can take common, these are common, this is equal to this, you can take it out, this is equal to this, you can also take it out. What you get is that n1 cos theta 2 minus n2 cos theta 1 divided by n1 cos theta 2 plus 2 cos theta 1. So, that is equal to Rp. Similarly, you put all these things in Tp and you get Tp is equal to 2n1 already 2n1 cos 2n1 cos theta 1 divided by n1 cos theta 2 plus n2 cos theta 1. So, these are the Fresnel coefficients for p polarized light, p polarized. Similarly, you can solve it for s polarized light, and so this is what we have got. This is what we have got here for the Rp and for Tp. Similarly, you can solve it for Rs and Ts, and we see that amplitude, these are the amplitude reflection coefficients. So, you can basically calculate what is capital R and capital T. So, oblique incidence, if you consider the magnetic permeability, which we have not considered there, then it comes in terms of Z, rather you having the refractive index, and it can similarly be solved for that. So, to summarize this, we have boundary conditions at the interface of two media, and if you want to have a propagation of this wave from one medium to another medium, you must have to consider these boundary conditions, and they must satisfy at the boundaries, the electric and magnetic fields. And the propagation of a EM wave at the interface of two media we have studied, and we have found the Fresnel coefficient for p polarized light. Similarly, it can be found for s polarized light. That means that you have to solve. So, this was x, this was z, and the polarization was y. So, the electric field now is in y direction, perpendicular to the plane. So, you have to solve for this wave. The electric field is here, and now the magnetic field is here, h is pointing in this direction, and electric field. Then you have to see what happens at the reflection and transmission. This is a homework for you. Thank you.